Hi everyone, welcome back. So last lecture we looked at the electric field integral equation and method of moments. And we said that, okay, there is this Green's function in there and that has a singularity. So we need to deal with that, right? So today we'll look at a slightly different integral equation formulation, which helps us deal with the singularity. Okay. And this is very useful when we want to discuss scattering from metals. We'll see why that is. So today we want to discuss scattering from metals. Okay, and this integral equation formulation is called the magnetic field integral equation. Okay. So if you recall, the electric field in terms of the Green's function was I omega mu volume integral 3 over k r square. So I'm writing out the diagonal Green's function in explicit form, which we've seen before. Kr minus 1 times r hat dot j plus 1 plus I over kr minus 1 over k square r square I dot j e to the ikr over 4 pi r. And this is the full diagonal Green's function formulation. The problem with this is that there is a 1 over r here and a 1 over r square term here, which means there is a 1 over r cube dependence in this electric field. And that actually will cause a problem when we try to remove the singularity in this Green's function. Okay, so a better approach for metals especially, because you're only dealing with electric currents, is to use the magnetic field instead. So the magnetic field is volume integral ik minus 1 over r e to the ikr over 4 pi r times r hat cross j dr prime. Right, so given an electric current, the magnetic field is easier to compute because it doesn't have as many terms, and it also doesn't have this 1 over r squared term. So the only dependence is 1 over r coming from this term and 1 over r square coming from this term. Right, so it's a little bit easier, we'll see, to remove this singularity in this Green's function. Right, when r goes to 0, the Green's function goes to infinity, but the fields, of course, we know don't go to infinity. Right, so we want to remove that singularity, which we discussed in the last lecture, and that's what we want to do. So essentially, we want to formulate a integral equation using the magnetic field. So we do the same thing. We start with the total field equal to incident field plus scattered field, similar to the electric field. Incident plus H scattered, which comes from extinction theorem, right? And H scattered here is given by the surface integral because we're dealing with metals. So you only have surface currents, curl of G dot J, right? dr prime. So if I substitute this in by taking n hat cross on both sides, right, then I get n hat cross H total is equal to n hat cross H incident plus n hat cross surface integral curl of G dot J dr prime. Okay. Okay, and we also know that n hat cross H total is nothing but J for PC, right, at the surface. So we can substitute that in, and then that would give us our integral equation for the current in terms of the magnetic field. And that's a little bit easier to solve. Right? But the difficulty, of course, is that since we're on the surface of a PEC, I have some current here. The left-hand side, which is this, J of R, and inside the integral, maybe I should write that explicitly, curl of r comma r prime dot jr prime dr prime. Right? Inside the integral, you have g of r prime, right? So in order to solve this, you need to equate these two at some point, right? At some point, r will be equal to r prime, and there, this Green's function, the curl of this Green's function, the Green's function kind of blows up to infinity. So we want to remove the singularity, okay? So in order to remove the singularity, we will look at this term and try to evaluate it a little bit carefully. And we looked at what removing a singularity means the last time, right? Similar to how a sinc function, we define it as sine x over x when x is not equal to 0 and it's equal to 1 when x is equal to 0. So by redefining the function, we can remove the singularity. Similarly, we'll do something like that, where when the singularity exists, we'll evaluate it separately. And when you don't have singularity, you evaluate it using your regular Green's function. Okay, so let's do that. So what we want to look at now is removing the singularity. Okay, so I want to deal with this n hat cross surface integral curl of g dot j term dr prime, right? So the way you deal with it is that you say, okay, your surface is something like that. And, I'm looking at, let's say, r prime, which is here. Right? So when r is equal to r prime, let's say this is my r vector. Right? As this vector kind of moves closer and closer, the singularity starts to appear. Right? So if I'm integrating, let's say, if I'm looking at r as it moves through, instead of going through the singularity, what I will do is I will deform this a little bit and go around it. Okay? So just bear with me, I'll explain what that means. So let's say, I deform around the singularity. Uh, say I deform that way, okay, into a hemisphere. So this is a hemisphere. So the surface is kind of deformed into a hemisphere. And then my R now would then be on this surface, right? So since now R is on that surface, R will never be equal to R prime. And that surface is a hemisphere that is centered at R prime. Okay, and then what we do is that we evaluate this integral. So this is A, let's say, which is R minus R prime on this surface. We evaluate this integral in the limit when A goes to 0. So limit A goes to 0. Rather modulus of A goes to 0. So in that limit, these two surfaces are the same, the original surface and this surface. Right, so if you take the limit, that gives us a similar to taking the limit of the sinc function as you're coming in. Right? So this is your sinc function and there's a singularity here. You take the limit and you see what the value is as you're reaching, and you assign that as the value. So similarly, we have this thing, take the limit as it becomes smaller and smaller, and we see what value it's reaching, and that we assign to the singular value here. That's the trick. Okay, so that's the basic idea. Let's actually go through the calculation, the mathematics, see how it works out. Okay, so I'm saying that this integral is nothing but equal to, so let me actually move this. Move it down here. Okay. So I'm saying that this is nothing but equal to limit A tends to 0 of n hat cross S minus SS. We'll discuss what these different S values are. curl of G dot J dr prime plus n hat cross integral SS curl of G dot J dr prime. Okay, so S is my original surface. This original surface is my S. SS is, this is my SS. Okay, and the S minus SS, which is, let's call it this one, is, we don't have to label it actually. We'll just deal with S and SS. Okay. Okay, so in the deformation, S is actually this total thing. Okay. S minus SS. Yeah. So S minus SS will then be just this part, and then SS is this part. Okay, so that's what I've written down here. And so when I add those two, I go back to S, and when I take the limit, it goes back to this integral. So they're equal. Okay, hopefully that makes sense. Okay, so I'll divide this into two parts. N hat cross limit a tends to 0, integral S minus SS, curl of G dot J dr prime plus n hat cross limit a tends to 0, SS curl of G dot J dr prime. Okay, so this is called principal integral EI, and this is called the singular integral SI. Okay. So this is similar to the sinc function again, where this is the part which doesn't include the singularity, and this is the singular contribution. Okay. So the principal integral EI is equal to n hat cross limit a tends to 0. Actually, let me rewrite this. So I'll write it as n hat cross the surface with a dash, curl of G dot J dr prime. And this notation of this dash is actually the same as this definition that we had up there. Limit a tends to 0, S minus SS, curl of G dot J dr prime. Right? So this notation with this dash in here essentially is saying that you take the integral over S, but you remove one point. And the way you do that is by computing this quantity, where you take the integral as you limit towards that point. Okay, and then that limit is assigned to that point. So that's what the principal integral means. Okay, numerically, you essentially just compute it around that point. You don't compute at that point. Okay. But you also have to add a correction factor when you do that, which is a singular integral. That's what we want to evaluate now. Okay, so the singular integral is n hat cross limit a tends to 0, surface integral over SS now, curl of G dot J dr prime. Okay, and we want to evaluate this. So recall that curl of G, which we did when we did the Diodes-Green's function lecture, is IK minus 1 over A e to the ika over 4 pi a hat cross I, where we use capital R instead of a, but they're the same thing in this case, right? A is r minus r prime. Okay, so if we use this, substitute that into our SI, then SI becomes n hat cross limit a tends to 0, integral over SS, ik minus 1 over 8 times e to the ika over 4 pi a hat cross j, a square sine theta d phi. Because it's a hemisphere, the surface, so the integral is only over theta and phi. Okay, so now when you take the limit, what happens, right? You have this a square term, and you have a 1 over a square term here, you have an a here and an a here. Let me actually write one more step and then we can simplify it. N hat cross limit a tends to 0, integral over SS, ika minus 1 over a square, or rather multiply the a as well both sides. So it would be ika minus 1 e to the ika over just 4 pi a hat cross j sine theta d phi. Okay, so what happens to this? Right, when I take the limit, this goes to 0. This term goes to 1. What happens to a hat? Right, so if you recall, a hat is what? I have the surface like that, right? And our a is this vector, a hat. So this can always be decomposed into a component that's normal to the space and tangential. Right, so for example, if a hat was this one, then that would be the normal component and that would be the tangential component. Right, so if you look at this, you have a normal component and you have a tangential component, right? The tangential component is in the same surface, same direction, on the not the same direction. So the tangential component is along the same surface as J, right? J is also along this surface, and this tangential component is also along that surface, which means A hat cross J, the tangential component, would be normal to the surface, right? And that cross N, which is also normal to the surface, would be 0. So does that make sense? If I decompose A into a tangential component and a normal component, a tangential component cross J becomes normal, and that cross N becomes 0. Right? So in the limit, you only get a normal component to A. Only this component survives, right? Because this cross J is in plane, and that cross N becomes out of plane again, becomes in plane again. Right? So in the limit, you only have a normal component, and a normal component would not be nothing but n hat. Right? Because in the limit, that becomes normal to the surface itself. Okay, so if that makes sense, then essentially you're left with minus n hat cross j, and you can bring j outside the integral because in the limit, that hemisphere becomes very small, which means j is constant over that hemisphere over 4 pi, integral 0 to 2 pi, 0 to pi over 2, which is the hemisphere angles, sine theta d phi. So you know this integral over a full sphere is 4 pi, which means for a half sphere it should be 2 pi. And so that 2 pi and this cancel, and you're left with 1 over 2. Okay, so this becomes minus n hat cross j over 2. And now you can use the triple product cross product rule. which is sometimes known as the back cab rule. Write this as 1/2 of minus n hat dot j plus j n hat dot n hat. Right? And what is this? When I take n hat dot j, that should be 0, right? Because n hat is normal and j is tangential. So this is 0 and this is 1. N hat dot n hat is always 1. So that gives us a very nice result that this is nothing but j over 2. Okay? So the singular component is just equal to j over 2. Now if I put this back along with the principal component into the original differential equation, integral equation, which if you go back, which is this one, right? So we still have this term. This term was decomposed into the singular part, which had the principal integral, and this into the principal part, which had the principal integral. So it was the principal part plus the singular part, which is just j over 2. Right? So that's what I'm going to write down now. Plus j equal to 2 times n hat cross h incident plus 2 times n hat cross curl of g, sorry, not curl of g, gradient of g, little g, r comma r prime cross j, r prime dr prime. Let me actually rewrite that. J equal to 2 times n hat cross h incident plus 2 times n hat cross principal integral over the surface curl of little g r comma r prime cross j of r prime dr prime. So why did I put gradient of g instead of curl of capital G? We showed that in the in the Dirichlet's function lecture that capital G, curl of capital G is nothing but gradient of little g times I, right? So, sorry, it's gradient of little g cross with I. So when you put that in here, this is what you get. Okay? Okay, so this is a very useful result. Why is that? Because this is now your integral equation without any singularities. Right? The singularity in this integral has been removed because that's what that represents. And that gave us another component which was moved to this side and essentially brought this factor of 2 everywhere. Okay, so this is called the magnetic field integral equation, and it's much better to use this when you want to do scattering from metals. So now you can take this, you can expand your J in basis functions and do the method of moments approach to solve it, right? Which is what we briefly talked about in the last lecture. Okay, so now we can start making approximations. So integral equations and method of moments gives you a full wave solution, which means it's true exactly, as long as you obviously choose the right basis function and expand it correctly. It can give you an exact result. Okay, but we don't often need such a computationally heavy tool for some problems to solve what the scattering is, right? So if you want to find scattering from metals that have certain approximations that you can make, then it might be simpler than doing the full wave solver. What kind of approximations? So one approximation is locally flat. If you have a metal that's locally flat, right? Approximation. Okay, so essentially I have a metal whose surface is locally kind of flat. Okay, so when it's locally flat, we know gradient of R, the gradient of G is some constant times gradient of capital R, which is nothing but R hat. And we saw this in the diagonal Green's function lecture, right? So if I'm at some position here, let's say this is my R prime, and I'm very kind of on a flat surface, and this is my R, then R hat, which is in this direction, would be close to being tangential, right? That's not true if I have something that varies very rapidly or very randomly. Let's say even if I'm here and I'm looking here, then R hat points this way, whereas the tangential component is like that, right? So R hat is not along the tangent when something is rapidly varying, okay? And if you go back to this integral, the contribution of this integral on the right to the current is actually somewhat local, which means that if I'm looking at the current here, contribution of other currents to that current only happens locally. Essentially, that comes from the fact that if I have a current here, and the current here that's radiating also contributes because it produces a magnetic field here. And that magnetic field contributes to this current. And that's why it's an integral equation, because the current anywhere is related to the current around it. Current there is related to current around it. So that's why you have this kind of current quantity inside the integral as well. So what I'm claiming here is that when it's locally flat, and even otherwise, contribution is usually fairly local. You don't have contribution from the current out there all the way out here. So you really only care about things that are nearby. So in the neighborhood, if it is somewhat flat, then your gradient G is along capital R hat. Okay, that's the claim. That's the approximation. It's important to understand the nuances of that approximation. Okay, so under that condition, your R hat is kind of along the tangent, right? It's kind of along the tangential component, which means this one is kind of tangential, which means this is along n hat, right? Because both J and this are not tangential. And if this is along n hat, then this whole thing goes to zero because you have n hat cross n hat, which is zero. Right, so essentially under the locally flat approximation, you can ignore this contribution. Okay, and then you get a very simple form for the current, which is that J is equal to 2 times n hat cross H incident. This is a very, very powerful and useful approximation because it essentially reduces an integral equation, not even having to solve an integral, right? It directly gives you what the current is in terms of the incident field, right? So you have essentially some incident field coming in. And I'm saying that the current on the surface is given directly from the incident field as 2 times the tangential component of this incident field, right? But we know that J is also equal to n hat times the total field, n hat cross the total field. This is the boundary condition, right? So essentially I'm saying that on the surface of the metal, H total is equal to 2 times H incident. Which means what? The reflected field, or the scattered field, if you like to call it, or H scattered, is equal to the H incident, tangential component. So I'll say tan. I mean, there is no normal component if you're kind of in free space and you have a metal, right? Because B, the normal component is 0. And in free space, at least, or in a homogeneous medium, isotropic medium, B and H are in the same direction. So I can just say the total reflected field is equal to the incident field. Okay? Strictly speaking, that's not true, but in most cases, it is kind of true. Okay, so this approximation, of course, is usually introduced kind of directly, but now we've kind of derived it from the integral equation itself. And we've seen that under locally flat conditions, it comes out. Okay, so this approximation is called physical optics. And it's a very powerful tool in designing and analyzing or simulating reflector antennas, right? Because let's say I have a feed on some kind and have a big reflector. How do I actually find the field radiated from this reflector? What you do is, the horn fields. Now we've seen how to do that in HFSS. You can extract it on this air box. And then from those fields, use field equivalence principle to find the radiated fields everywhere in space. That gives you the incident field on this surface, right? You can find that from the Diode-Green's integral. Once you know the incident field here, you apply physical optics, and that gives you the current distribution on this surface. Once you know the current distribution, you can use extinction theorem, remove the reflector, and find the free space radiation everywhere. Right? That gives you the scattered field. And then you add to that the incident field as well, which is coming directly from this source, and that gives you the total field everywhere. Okay, and that's how you can find reflection from a reflector given some incident wave. It's very powerful, that's why, without having to do any integral equation solver or finite element or any kind of complicated technique. You can even implement this yourself, which I have done in the past for my own research. Okay. So that's about physical optics. We actually want to look at physical optics a little bit closer and see, can we simplify it even further, right? So let me ask you this. So I said that I have a horn antenna, I have a reflector, right? Let me make a copy of this. Make another copy here. Same scenario. So physical optics says that, I have some source here, it's putting out field, and you find the field everywhere over this reflector. And once you find the field everywhere, then what you can do is you can use that field to find the radiated field everywhere using physical PO approximation. PO is physical optics. Maybe I should write that down. Okay, so if I want to find the field, say here in space, then I know the current everywhere on this surface now from PO. Now I find the contribution of all of that to this location using the free space Green's function, right? So you essentially integrate over all of these points on the surface, and there's the contribution from all of them. Right? Okay, the problem with that is that we know from geometrical optics or ray optics that if I have a reflector, then any ray that hits it satisfies Snell's law of reflection, right? So it reflects off like that. Have another ray like that, maybe that reflects like that. Have a ray here, it goes that way. Have a ray here. I don't know, maybe that goes that way. Something like that, right? Or if you like, this is parabolic maybe, and I'm putting my reflector, my horn feed on the focus, then all of these rays kind of go out parallel. Something like that, let's say. Okay, which means what? Which means that if I look at any point, observation point, the same observation point as this one, only one ray contributes to this, right? There is only contribution from the field that went and hit there and then passed through this point, right? So essentially only contribution comes from this location, not from everywhere. But physical optics has said that it comes from everywhere. So how do you resolve this seeming contradiction, right? Where physical optics says I have contribution from everywhere, whereas geometrical optics or ray optics says that I only have contribution from one point. Okay? That's what we want to do next. So the claim here is that even in physical optics, when you actually compute this integral over all of these points, all of them cancel out, and the only major contribution comes from this location where the ray reflects exactly using Snell's law of reflection. So contribution from all of these guys cancels each other, and you only get a contribution from this location. Okay, so that's called the stationary phase approximation. Approximation. Okay, so let's look at that a little bit more. So what I'm saying is that, okay, I find the path length for this ray, find the path length for this ray, find the path length for this ray, then for this one, and so on. I find the path length for all those rays and I plot them out. What would that look like? So you'll see that, let me use black instead. So I'm plotting now. So these are my rays along the surface, and I'm plotting the path length. Okay, if you plot the path length, you'll see a parabolic kind of shape. Okay, and the minimum path length, this minimum path length corresponds to the reflected ray. So this corresponds to this ray that satisfied the Snell's law. And we'll prove that right now. But essentially what I'm saying is that, if you take all the path lengths, all possible path lengths, and you plot them out, you'll see that the shortest distance is the one that actually the ray optics formulation follows. Okay, and that's called Fermat's principle. Fermat's principle is sort of more general. It says that in any propagation, a ray of light always takes the shortest path. So we have shown it we're kind of only describing it here in terms of reflection from a metal, especially from a smooth metal. But we still have to establish that, right? So why is it called stationary phase? Because if you look at path, this is the path length that I'm drawing here, right? That I'm plotting here. But phase is k times r, right? Where r is the path length. So it is in fact where this phase becomes quote unquote stationary or minimum. Right? Stationary just means it's not changing. Right? Here is kind of fixed. It means the derivative is zero. At this location, the derivative is zero. Right? So when the derivative of the phase becomes zero, that point is the point at which the ray, that point corresponds to the ray that actually reaches that point. So in the ray picture, it's when the derivative of the phase goes to zero. Okay. So this ray corresponds to the stationary phase point along this integral. And that's why the ray picture is physically makes sense, right? Because in reality, we know that it's not really a single ray. You have radiation everywhere that excites currents and those radiate. But you can approximate it by rays because only one point actually contributes to those integrals. That's the philosophy and the idea. Okay, so we do actually want to prove at least one result, which is that if you apply stationary phase approximation, you can essentially get this geometrical optics formulation. Okay, you'll show that applying stationary phase approximation gives you the result that when the phase becomes stationary, you get law of reflection. Okay, that ray essentially satisfies the law of reflection. That's what we want to show. So I've covered this idea of stationary phase and method of stationary phase in the past. If you want to look at the general idea and the relationship, you can go back and look at that in more detail when we did the Green's function of the radar equation in one of the videos I made in the past, but I'll just briefly describe the idea here. So what's the idea? The idea is if I have an integral that looks like this, f of x e to the I times phi of x, where this is slowly varying, and this is fast. Okay. Then you can approximate this as just as some coefficient. So let's say it's a x naught, some coefficient times the actual function only at x naught. Okay, where the derivative of phi at x naught goes to 0. So graphically, it looks something like this. So I have my, I have my phi of x naught, phi of x. So phi of x, use black. Phi of x, we said is maybe doing something like that, right? But if I take the exponential of phi of x, and I take the real part of that, if I look at the exponential term, that has to vary very rapidly, right? Because it wraps, the phase gets wrapped. And then at the stationary phase point, it slows down this fluctuation. And then again, it speeds up and becomes very rapid. Okay. So this is my x, and this is my phi to the, so this is phi of x, and this is the real part of e to the I phi of x. You can also take the imaginary part, doesn't matter. But essentially, because phi of x is varying and it's varying very fast, when I take put it into the exponential, you get a really fast sinusoid that slows down only when phi of x slows down and becomes essentially stationary. Right? So since I have something like this, what the idea is that all of these contributions, because it's varying so fast and the amplitude is not really changing that fast, right? All of these contributions cancel each other. So this part cancels this part cancels this part cancels this part, and so on, until you reach this location where the variation is so slow that they add up, right? This part doesn't have anything to cancel with. That's the idea. So if you actually compute this integral as a function of x, so if you do this numerically, you'll see that, it kind of, the integral itself fluctuates as you go through, right? But then there's this big jump when you go through the stationary phase point, and then again, it fluctuates slowly. Okay. And essentially, we're approximating this by ignoring that and just saying we only look at this part. Right? We ignore the small fluctuations from the cancellations. And we say that this is the value of the integral. Okay. And you can, of course, make all of this rigorous. The proof of this theorem of stationary phase approximations is in a book called by Papoulis, I believe. And I've given more details in the video where I explain it in a little bit more length, but that's the general idea. So we want to use the stationary phase approximation in the physical optics integral, or the integral for the current along this surface, and show basically that when this phase becomes stationary is when this ray that came in and went out, or this contribution from this path, follows Snell's law. Okay, that's what we want to establish. It's not fully deriving geometrical optics from physical optics. That's a longer derivation. But today I just want to kind of give you a brief derivation of just Snell's law from the radiation integral under the stationary phase approximation. Okay, so let's do that. Okay. So I'll call it geometrical optics. So we're kind of deriving one result in geometrical optics, which is ray optics, from physical optics. Okay, so I know that J is 2n hat cross h incident from physical optics. So I start from there. And the far field integral, which we saw before, is e to the ikr over 4 pi r, integral over the surface, j cross r hat cross r hat. And we've seen this a couple of times before when we did potentials, when we did the Green's function by dr prime. Okay, so what is the incident field? Right, so I'm interested in finding, say I have this parabolic surface and I have an incident ray coming in like that. What is the meaning of a ray? We haven't really discussed that, right? We'll see this later when we do plane waves, but essentially a ray you can think of as an incident plane wave coming in that direction. So if you haven't seen plane waves before, this might be a bit confusing, but just bear with me for now. I'll give you an expression for it and we'll derive that expression in the next lecture. Okay. And I have some reflected ray and I want to show essentially that under the stationary phase approximation, this reflected ray satisfies Snell's law, right? Now we have an incident plane wave coming in, incident ray coming in, that's my reflected ray. Or I should say this is my observation direction. It's the same thing because when in the far field, observation direction is parallel to the direction in which this ray has come out, right? Okay. So we want to show essentially that, what am I saying? I'm saying, okay, if this is my origin, then in the far field, this becomes parallel. In the far field, if I'm observing from the origin, it's the same thing in terms of r hat at least as observing from this point. So I'm observing in some direction and I want to show that that observation direction satisfies Snell's law, which means this angle is equal to this angle, right? For a given incident ray. That's what we want to prove. Okay, let's do that. So for a plane wave, H incident, the E incident, which we'll see in the next lecture when we do plane waves, is some E naught vector, constant vector, times e to the I k hat dot r hat, k hat dot r prime. Yeah, we'll see that later, but that's the definition of a plane wave in terms of the electric field at least. Okay, so let's assume you know that you've seen plane waves before. So which means that the incident field, incident magnetic field is 1 over eta k hat cross E naught e to the I k hat dot r prime. And that also is based on the definition of plane waves. So now what I do is I substitute this term into this. That gives me j. Then I substitute j into this. And then I'll have my integral over surface. I'll have the exponential term, which comes from this factor and this factor. And then I have some other amplitude term in front of it. But I'm really interested in the exponential term, right? Because we need to make that stationary to get the relationship that we're looking for. So I'm going to skip the amplitude terms and just say that the phase term inside the integral, phase term is e to the I k r prime dotted with r hat minus k hat. Okay. So I have my e to the r prime r hat and e to the r prime k hat. And that's what I have here, e to the I k r prime r hat minus k hat. I can put a minus sign here, I guess, just to be exact. Or you can write k hat minus r hat, doesn't matter, because anyway we need to send the gradient to 0. Okay, so this is my phase term, and I need to see where this becomes stationary, right? Which means where this becomes stationary. And now we are on the surface of we're on a 2D surface, not on a line, right? Which means we need to find the gradient of this term along the tangent, or we need to do the derivative along the tangential direction and set that to 0 for all directions. Right? So if I'm on the surface of this plane, then I need to make sure the tangent, the directional derivative along all directions on this surface are 0. Okay? So if I define this phase term as phi of r prime as r hat minus k hat dot r prime, which means I'm saying this is nothing but e to the ik phi r prime. Then I need to set this one such that its gradient along r prime must be 0. Gradient dotted with some tangential direction must be 0. And that's the direction derivative. So the gradient doesn't have to be 0. The gradient along the tangential direction must be 0. Okay, that's what it means for the phase to be stationary, because in the integral, we are moving along the tangential direction when we integrate over the surface. Okay, so only this has to be 0. That means what? That means that gradient of phi must be some lambda n hat. Right? It must be normal for some lambda. For some lambda. Right? We need to find what this lambda is. Okay, so gradient of r hat minus k hat dotted with r prime is actually nothing but r hat minus k hat. Okay, because this gradient is with respect to r prime. Right, so you can try this for yourself if you like. You can take the dot product of two vectors and take the gradient with respect to one of them, and you'll get back that one of the vectors, the vector, this vector. Right, so it's essentially, you can write gradient of this is equal to a, right? Because you have ax x plus a by y plus a z z. Take the gradient of that, that's just ax hat plus ax x hat plus a by y hat plus a z z hat. Okay, and that's what I'm applying here. Okay, which means what? Which means that r hat minus k hat is equal to lambda n hat. Okay, and I want to find what is lambda. So to do that, I can say, modulus of r equal to mod k plus lambda mod n, put squares in there. No squares, sorry. Right, plus 2 lambda k hat dot n hat. Okay. Okay. So I'm equating the magnitudes on both sides once I take k hat to the other side. So that means that 1 equal to 1, because that's what the magnitude of r hat and k hat is, plus lambda plus 2 lambda k hat dot n hat. These two cancel. So you end up with lambda times, there should be a lambda square here. Oh, sorry, these do require square terms. Lambda square and square. Okay, there we go. Okay, so I have lambda, the square should be on this term. Okay, so lambda times lambda plus 2k hat dot n hat equal to 0. And of course, lambda is not 0. The non-trivial solution to this is that lambda equal to minus 2 k hat dot n hat. Yeah, I can substitute that back in here. I'll substitute this back in here. And that gives me a relationship between r, k, and n hat, which is what I was looking for. Which is that r hat is equal to k hat minus 2 times k hat dot n hat along n hat. Okay, and this is in fact exactly Snell's law of reflection. So typically you learn Snell's law of reflection as theta I equal to theta r. Right? And that's also correct. This is just a different way of writing it. So to show you why, you can look at what this means. Right, I have my incoming direction. Say this is k hat. And then I have my n hat, which is along this direction. So this vector, which is, let me say, this vector, right, which is the projection of k hat onto n hat. This vector is minus k hat dot n hat. So that would be the length of the vector. You need the minus in there because you really want to project the positive part, positive direction of k onto that, right? So that projection times n hat, right? That is that vector, because this length is equal to minus k hat dot n hat, and you multiply with the unit vector in that direction to get this vector. Okay, so I add that vector to my k hat. So then this vector, which I can write in a different color. So this vector is k hat plus minus of k hat dot n hat times n hat, right? And if I take a copy of it, so I take another copy. So this is k hat minus of k hat dot n hat times n hat. And I add it to this vector. Now I add this one and this one, and that gives me this vector, right? So I'll use a different color. So this one would then be this plus this, which is exactly equal to r hat, which I call r hat is k hat minus 2 times k hat dot n hat times n hat. Okay, and that's what we've shown here. So where does Snell's law come in? Snell's law comes in because this length and this length are equal, right? That's how we got this relationship. If these two lengths are equal, then these two angles must be equal. Okay, so this is exactly the same thing as Snell's law of reflection. Now, of course, Snell's law of reflection also applies to dielectrics, which we'll see in the next lecture or a couple of lectures down, once we do plane waves and we do reflection from dielectrics. But what I wanted to show you here is that you can derive Snell's law as from the stationary phase approximation applied to the physical optics integral. And that's a very nice result, because essentially we are saying that ray optics is an approximation to physical optics, which is an approximation to the full wave integral equation. And it's important to kind of remember where these approximations come in and how where they apply. So what are the kind of limitations of physical optics and geometrical optics? So PO and GO are closely related, which means they're both pretty good approximations that you can use. PO, of course, is a little bit better, but computationally more heavy. So PO and GO do not account for edge diffraction. It's important to remember that. So what does that mean, right? So if I have just a metal plate or a metal sheet, and I have some incident radiation, say I have a source there, some rays come and hit this, like that, right? And then of course they reflect off. Using using ray optics, you can just use this, or using physical optics, you integrate the whole thing. But keep in mind that both geometrical optics and physical optics, they are local. So for example, when you find the current here, you only look at the field here, the incident field here. But that doesn't account for the fact that next to this, there is no metal, right? So it doesn't really apply. It doesn't really know that this is kind of an edge, right? So we know that at an edge, to satisfy the magnetic field boundary condition, which is that the edge should be tangential, the curl of edge here is very large because it has to bend quite significantly or very fast in space, right? Because the curl of H is large, the currents on the ends would be very large. So if you do the full wave solver, you'll see that the currents actually become very large towards the ends. Something like that. Maybe it's like something, it's something like this, and maybe a little bit more there, something like that, right? They blow up. But physical optics will just tell you that the currents are like this. In the middle, they're slightly stronger because it's closer to this point, and the ends it's a little bit weaker. Right? But this profile is essentially the same profile as the incident field. It doesn't account for this edge diffraction at the ends. And the same is true for geometrical optics. Right? Because it's a local thing, it doesn't know there's nothing out here. So it can't use that approximation. So to fix this, what people have done is that they say, okay, I don't want to go all the way from PO back to integral equation and solve something very complicated. I only want to treat this edge case, right? These edges. So they introduce a correction factor, which is called the physical theory of diffraction, which places these currents on the edges, these large currents on the edges. Okay? Because we know there's an edge there from the mesh or the geometry. So we can place an additional current there, which satisfies the continuity of the current and the boundary condition, that there is no metal beyond that, such that that correction factor gives you a more accurate field. So it's somewhere between, midway between PO and integral equation, right, in terms of accuracy. So this one is a correction factor that is current based. Okay. Another correction factor that you can add is to GO, which is called the geometric theory of diffraction. So that's a ray-based correction factor where I know there's an edge. So I assume that basically beyond this edge, there is scattering in all directions. Right? And these are diffracted rays that are added to the model. And that essentially produces some field from the backward direction. We know that there is field in the shadow region. So in PO and GO alone, this is all shadow region, right? No ray reaches this part. But with GTD, you can actually get rays in the shadow region as well. So I'm not going to go into details of PTD and GTD here. That's kind of beyond the scope of this class at least. This is ray-based, but it's just an introduction to tell you what this is. And this is the basis. GO plus GTD is the basis for SBR plus in HFSS. Okay, so if you go into HFSS, you'll actually see that there are correction factors you can add to SBR plus. One of them is PTD. Another one is called UTD, which is you can think of it as an upgraded version of GTD. It's called the uniform theory of diffraction. And another correction you can add is called creeping waves. And we'll discuss creeping waves much later in the course when we do scattering from spheres. But SBR plus is essentially something like GO plus GTD. Okay, it's a little bit more complicated than that, but this is the backbone of SBR plus. Okay, that's a solver that can solve very large electromagnetic problems, right? Like scattering from very large structures. Because these correction factors can actually be quite accurate, right? So they're really fast and much faster than MOM, for example. Okay, so this gives us a nice place to stop in terms of today's lecture and also the large number of topics we've been discussing over the past few lectures, which is this Green's function and radiation integrals and computational EM. Because we've essentially covered the basis behind a large chunk of computational EM, which is integral equations, method of moments, physical optics, and geometrical optics. Geometrical optics, we haven't really done much. A very brief kind of perfunctory introduction to it, deriving from PO. We haven't done a full derivation. We haven't discussed what the iconal equation is or any of that. But for now, this is probably a good place to stop. So this is a good stopping point also because this is sort of midway in the course in terms of material. So in the rest of the class, we'll take a quick break for 1 week or so and then come back. And the rest of the class, we'll switch topics and start discussing plane waves. We will discuss waveguides. Then we'll do a little bit of computational EM again towards the second half, which would be finite element in that case, which is the other big computational EM topic apart from MOM. And at the end, we'll also do some scattering and some advanced topics. Okay, so that would be the second half of the class. Okay, so hopefully it was interesting and covered a bunch of stuff today. Just to recap, we did magnetic field integral equation, which is a more stable version in order to solve scattering from metals. And then we saw that approximations to MFIE is physical optics. When you have locally flat approximation, you can make the locally flat approximation. And then we said physical optics can further be simplified by using stationary phase to give us geometrical optics. And we showed that we can derive from that Snell's law of reflection. Okay, I'll stop here and I'll see you in the next one. Thank you.